Okay, so let's talk about surface area. So a surface can be generated by revolution, very similar to solids. So here's an example. See that red, there's that red function. And then this is revolved around the x-axis. And so rather than a solid, just think of that curve creating a shell, just the shell, and we want the area of the shell. Okay? So in your geometry formulas, you're not going to find the area of that, right? So that's the idea. Functions can be any curve, and then we can generate a surface. And if most functions don't have a nice, tidy geometric formula to go with them. But we've got the tools to do this. So if S is a surface area function, two questions. What would S of A comma X mean? And then just in the very most general sense, could you write a rule for the surface area function? In the very most general sense. You know, we haven't attacked it, investigated it, and broke it down, but you still should be able to, in a very general sense, write how we're going to do that. What is going to be the rule for a surface area function. So why don't you just, for 30 seconds, talk to the person next to you. What does that S of A comma X mean? And what would be a general formula for the rule for the function? Go. Okay, so what would S of AX mean? What would that represent? Any volunteers? What would S of A comma X mean? What would that mean?
So is that the arc length if we just stretch that whole curve out?
Okay, so it's the arc length. Is it arc length? But what does this mean? So what would this mean? If S is a surface area function, right? So capital S is a surface area function, then could you describe what would that notation represent? Seth, way in the back. Good. He said the net accumulation of surface area starting from x equals a up to our independent variable, right? So we imagine surface area being swept out from starting from a, and any x that you pick and stop, you get that amount of surface area so far, right? That amount of surface area so far. Okay, and what would a general rule be? Someone else? Can I write it down? Can you write it down? Give it a shot.
The
Integral
from
a to x.
To pi f of
We don't know the details yet. Okay. So what can we say though? For sure. Rate of change, right? Rate of change. We can say that as r sub s of something else dt. I hope the success rate was high in that, and that you were just being quiet. We've done this a million times now, right? If you want a net accumulation of something, it's the integral of its rate of change function, right? It's the integral of its rate of change function. And so what's going to be our main goal here? What is the rate of change of surface area? What is the rate of change of surface area? Same thing over and over again, right? Over and over. If you want the net accumulation of some kind of quantity, we're going to integrate its rate of change function, and that the rate times a little change in our independent variable gives us a little bit of what we're accumulating, right? Y equals mdx. And then we're going to accumulate all those little bits of our quantity, right? All those little dy's. Each one calculated by mdx. Okay, so let's look at that. So here's sine x, and I could flip it around. Let's talk about flipping. Just think about flipping sine x around the x-axis. Okay, and then when we do that, we get, you can imagine the surface we'll get, something like that. Okay, and as before, what did we do? We filled it up. So here's using what? Dx, right? Dx through delta x intervals. And when we did volume, what did we do? We found the rate of change of volume by looking at the rate of change in the current interval of one of those cylinders, right? So how could we, if we looked at this, what might we do to instead of building a volume, accumulation of volume function, what might we do to build accumulation of surface area? Again, thinking about in the current interval. So here's the current interval, it's the dark blue one, right? So if we're thinking about building surface area, what do you think the rate of change is? Yeah.
Instead of using the area of the base as our rate of change, we're
Okay.
using the perimeter instead.
So just looking at the outer edge, right? So then what is the rate of change of these cylinders as they're growing? What's the rate of change of these cylinders as they're growing? Instead of being the area of the base now, if we're just thinking about the perimeter, then it would be 2 pi r, right? Maybe? So let's try that, right? So then we think about these things sweeping out in the current value, in the current interval. And it's basically that rate of change of the shell or the outer edge looks like it might be just the circumference of that cylinder, 2 pi r. So let's actually try this with something that we know the surface area of and see if it's right. Okay, so let's do, instead of doing sine x, so we have no idea what the surface area of the sine x generated solid is, so let's do a sphere generated by a circle. Okay, so so if I were to, this is the circle with radius 3, so the function is the square root of 9 minus x squared, it's up here, okay? And so if we could build that function and then we get the surface area of the completed shell, and what should that be? So what we know that should be what? Surface area, anyone know the surface area of a sphere? Remember what that was? 4 pi r squared. Okay, but this is going to be for half, right? So half of a sphere would be 2 pi r squared, right? And so for this one, we know our radius is 3. So what is that? 18 pi. So when we do this, we ought to get 18 pi. And what do we think the rate of change is? So what's our rate of change, do we think? How is each one of how are those shells changing? By do we say? What do you think? So right here, so we're looking at in the current value of x. Maybe red will show up. I doubt it though. It's really dark. Does that show up? Barely. Okay. So our rate of change is 2 pi. And what is r then? What is r for that right there? What is that? That's the y-coordinate, right? That's the radius in the current value of x. The radius of that thing will be the y-coordinate, so it'll be 2 pi y, which is 2 pi times radical 9 minus x squared. So we've got our hypothesized rate of change, and we're going to do what? So no, can you set up the surface area for the half sphere function? Can you set up the surface area for the half sphere function according to our attempt here? So this is my surface of my half sphere. That's what I'm calling capital S of the half sphere, or the accumulation up to the half sphere. So what would it be? Anyone got it? Got the rate of change of surface area. We want to write the net accumulation. Everyone should be able to do this now. In the back, please. So let's go ahead and define the function as, what is the function? The function is 9 minus x squared, right? And then I can do 2 pi times f of t. What about typing in square root of 9 minus t squared right now? It works too, but it's not as efficient, right? Not as efficient. So this goes to the last page, the free response of about the tweets, right? Do the most efficient thing, right? So don't use square root of 9 minus t squared. Use f of t, and then dt. Okay, did you get it right? Almost. A, right? A to x. And what are we interested in? So we're checking to see what? What's that? 0 to 3. She wants 0 to 3. So I'm going to put in Control-Shift-I, the integral from 0 to 3, right? Of 2 pi f. Is this right? Right. Use function notation. This is another huge thing. So huge part in this course we've been trying to get you to see is the efficiency of function notation. I've already defined this function. I don't have to rewrite the integral. I can instead just do what? S sub h of s of hs of 0, comma 3. I got 44, and what was my surface area? 18 pi, is that right? What happened? Yeah. No, so we're just calculating that, so that flat, yeah, so both of our calculations, we did half of a sphere, which would not include that, right? And then when I did by integration, it's the same thing. It's starting here and going from here to here. So neither of those included that. Neither of those included the circle on the left side of that solid, or the shell. Yeah? Okay, why? So what was our rate of change function? Circumference is 2 pi r, not 2 pi r squared, right? So that's okay. So the problem here is not any little mistake that we made. According to our premise here, everything we've done is correct, algebraically and computationally, and all the expressions are right. So the problem is the assumption we made at the beginning. So this is fundamentally flawed, and we spent the time, so you get the point that this doesn't work. Why doesn't this work? So what assumption did we make that this is flawed from the start? What we did? Any ideas? Yeah. So when delta x gets small, is that what you're saying? When delta x gets small, we'll adding up, accumulating all these little, they're like horizontal ribbons, right? Are they gonna, even as things get small, is the sum of all those horizontal ribbons gonna sum up to the same as the surface area? No. Okay, so no. So why not? That's the question. Why not? Because so we're gonna think about making the dx small. So, all right. So here's making the interval smaller and smaller and smaller. Why is this still not going to work? What's that? It's because we're always adding up. We're always adding up these like horizontal segments, and that's not going to do it. No matter how small you make them, really what we want to add up is what? No matter how small we make them, we're still going to be adding up little horizontal pieces that have been wrapped around. What is it that we want to really get the true surface area? Yeah, so really what we want is we need to do it based on arc length. Instead of like the base, think of those all as little right triangles. We can't, if we add up all the bases of those right triangles, it's not going to work no matter how small we make them. What we need is the hypotenuses of those right triangles. And then when that gets small, that's going to be a nice smooth curve, just like the circle of the sphere. So our problem was our assumption that delta x is going to do this, right? You've got to do it not in terms of x, but in terms of ds. Not dx, but ds, like we did on Friday. So instead of our ribbons looking like this, we need them to look like this. So the question is, where do these come from? How do we, do you see the difference in my very poor diagrams? We need to start with an edge, like an arc length edge that gets rotated around, not a horizontal edge that gets rotated around. So those elements that we need come from a cone. So let's take a look at that in the text. So if you split a cone, you can flatten it out. Okay, you can flatten it out like that. So what we want to get our element is we want a piece of that, which is called a frustrum. Frustrum, because it's kind of frustrating to try to say it, right? A frustrum is like one piece of a cone like that. And do you see that that's gonna be like the elements that we need, right? Because it's got the angled side, which is like our hypotenuse of our little triangle that we used for arc length. So that likewise can be cut and flattened out. And that's going to give us, that will be our little piece of area. So that's going to be our little piece of area of which we're going to accumulate, right? We're going to accumulate those areas. Not, what about the ones we tried? We just tried, you know, ribbons that we could just flattened out like rectangles, right? Doesn't work. So we need these little pieces of cones that we're going to flatten out. And those are what we're going to need as our accumulating elements. All right, so if you see here, here's our sign, going back to sign. So rather than taking horizontal segments and flipping them, we need these angled segments. And then as things get small, watch what happens here. So here's a smaller delta x of 0.5. And then it's 0.1. So you see when things get small, now those frustra, so plural is a frustra, they're going to match that surface perfectly when things get real small. Okay, so here's one of those. Here's one of those, again, based on ds, right? The little line segment connecting the points of the curve, rotated around. So what we need is the rate of change of those, what the rate of change of those growing is. So when you take one of those and flatten it out, its perimeter is the 2 pi fx. That's what we had, right? 2 pi fx. But now, this dimension is our little bit of arc length, right? That's our little bit of arc length, ds. So this is what's going to kind of frame how we get the rate of change of surface. This thing, not just a flat rectangle ribbon. Okay, so what is that little piece of accumulated area then? So ds equals what? D capital S equals what? We've got the perimeter and then this dimension, right? So what does capital ds equal? Or D capital S, I should say? How would you write a formula for that? So a little accumulation of surface area would be what? So what we had 2 pi f of x dx, right? dx. We need 2 pi f of x times ds, right? 2 pi f of x times ds. That's what we need for a little accumulation of area. We had dx, right? We had dx. We need ds. Okay? So then what is ds? ds is what we found on Friday, right? ds is, it's that hypotenuse that we worked on, right? When that triangle was accumulating and we let dx grow to 1, then we got this as the hypotenuse, and then times whatever change in x is. So that's our ds, is all that stuff. And so that gives us the rate of change right there. So now we've got the rate of change of surface area with respect to x, which we can write r sub s. So that's what we need. We need this extra piece here to give us, to base these frustrum, each frustrum on arc length, not on dx. And so we've got it. So now we can start applying this to problems. So now let's try this with our sphere and see if we get the right surface area of the half sphere. So can you write, let's go back to that one. So now the picture isn't right, but we're going to get the math right now. So imagine instead of it looking like that, the tops and bottoms of all these are now from the cone, right? They're frustrum. Each one's a frustrum, and they're angled, right? So it'd be more like this. Angled, boom, 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 boom. Okay? And so now I want to do what? Which line do I want to adjust here? First, second, third, or fourth line do I want to change? Which is the first line? How do I want to change it?
Put in parentheses the 2 pi f of t.
What's that?
Put in parentheses the 2 pi f of t.
Okay.
And then the square root
I need the square root, right? Of
1 plus
1 plus. I need the derivative of f squared with respect to t, right? So I can do, actually, I could define another function r sub f and use that, or I could just go right to the math menu and do total derivative of f of what? T, but then I need d dt, right? And then I need what? That thing squared. And should get the exact same thing now as the 18 pi. Now it works. So now I've got the right surface area of that half sphere that we know is 18 pi, 56.5487. Okay, so there's a little bit of a difference here. So GC uses numerical techniques to calculate these values, right? It's making intervals very small and actually doing a very close approximation. And as it does that, in this particular case, it's off by a little bit, but close enough to know that we've got it set up right. Okay? Any questions on that? Okay, so let's look at an example here. So how about if, I'll start a new GC file. Any questions on surface area, developing formula, rate of change, the half sphere? Any questions before I go on? Okay, so let's look at a new function. I'll call it g. And it's going to be 2 minus 2 equals 2 minus 2/3 x. Okay? So let's graph that. From 0 to 3. And I want to rotate that about the x-axis and find the resulting surface area. And what will I get when I rotate that about the x-axis and find the resulting surface area? What will I be talking about then? That'll be a cone, right? That'll be cone, and that's another one we can check, right? So the lateral surface of a cone has the formula area. Lateral surface of a cone is pi times r times s being this length here, which is pi times r times square root of r squared plus h squared. That's the hypotenuse, right? So this would be our, if we're rotating this way, right? We're rotating this way, then this would be our height, and this would be our radius. So we want to set up the accumulation function for surface area, and then we want to check the completed surface area against the area of the lateral surface of the cone. So can you write down the so we'll call this S sub C. And by the way, so last time we were talking about how we could just have these defined in terms of x under the assumption of what the a value is, or we can do the a comma x. So from here on out, we're going to always do the a comma x, right? So are they both variables? No. A is parameter. A sets up a particular situation, and then X varies starting from A. So A is a parameter, X is a variable. But they're both arguments that we can change, right? Okay, so what will this integral be? What will this integral be for this arc, or this surface area function for this particular cone? Somebody new, can you tell me?
Real quick, Bill.
Yeah.
A can start anywhere, right?
Right, so yeah, so we'll do it generic, we'll do the generic function, and then we'll check our particular cone that we have, the one that goes from 0 to 3.
I just didn't get why it wasn't a variable. Then if they could start.
But so you pick it, and then in the situation now it stays fixed, right? You pick a starting value, and then X varies. And then you can pick a new A, but now it's a new situation. So that's the difference, right? So a variable is truly varies in the given situation, whereas a parameter is fixed in the given situation, but then can change from situation to situation. Does that make sense? Yeah. Okay. Sean, did you get this function? So 2 pi what? G of x, okay. What's that? Derivative of g, right? Derivative of g. So I'll use total derivative here. And that whole thing squared? Okay. How do you do? Perfect, except, yeah, we need all these to be a different variable than the x, right? Everything besides. But yeah, but your formula is perfect. So let's use u. Just know that there's nothing special, magic about t. Okay, is that what you guys got? Missing one? Yep, right, thank you. And I guess I didn't learn that lesson when I was getting ready, because it happened to me when I was getting ready for class today several times. Why isn't this working? It's got to be d du, right? Switch to u. Okay, and then we want to get the surface area of the this completed cone that we would get if we rotated around the x-axis. So it's the integral of, use function notation. Who wants to write all that out? We just defined that. Now that's the point of function notation. And am I going to write out s sub c of a of x equals the integral and then do the whole integral? No, right? Just that thing on the left represents the function value that we want. So a equals 0, 2, 3. Okay, 22.6543. And we want to compare it to this cone right here. That's the cone we want to compare it to, which will have a value of, use GC, pi, radius is 2, times the s is the hypotenuse of the lateral side there, square root of 2 squared plus 3 squared, same thing. Got it. Okay, the question is, can we do that same problem in terms of y? Same thing, rotating around the x-axis, can we still do it in terms of y instead of in terms of x? And the answer is yes, but we don't have time.